Good morning or afternoon, depending on where you're joining us from. I'm Dean Christensen, the Digital Marketing Manager at GridGain Systems. I want to thank you all for taking the time to join us today for this very informative webinar, The Anatomy of an In-Memory Data Fabric. Your presenter today is Nikita Ivanov, the founder and CTO of GridGain Systems. Nikita has over 20 years of experience in software application development, building high-performance computing and middleware platforms, including, of course, the GridGain in-memory data fabric. He's a frequent blogger and speaker at industry events and is certainly one of the foremost thought leaders in the space. But before we get into Nikita's presentation, just a few quick administrative points to make. Nikita will be speaking for about 35 to 45 minutes, after which we'll have about 15 minutes for Q&A. You'll notice that just above the presentation screen is a questions button. Click there to ask a question at any point during the presentation. Nikita will respond to your questions during the Q&A segment. We may not have time to get to all of the questions during this event, but we'll definitely answer all of them afterwards. So please take advantage of this opportunity to ask the questions of the foremost leader in the space. You can also use these questions to let us know if you're having any technical difficulties, and we'll monitor those throughout the presentation. So with that, we're ready to turn the floor over to Nikita Ivanov. Nikita?
Yes, Dan, thank you very much for the introduction. Welcome, everybody. Good morning, good afternoon, good afternoon. What we're going to do in the next 35, 40 minutes, depending on how we go, we'll talk about the in-memory data fabric. What I typically do when we present on this topic, I want to spend the first maybe 10 minutes on talking about in-memory computing. What is this? What is it not? Some of the key characteristics of that, because what I learned over the years talking about in-memory computing is that it's a fairly confusing topic. And before we dive into the specifics of a product like GridGain Data Fabric, it's always worthwhile to kind of establish the base point for all of us to understand what, at least, from our perspective, is in-memory computing. After that, we'll dive into data fabric. We'll talk about the four major components that comprise in-memory data fabric from GridGain: clustering compute capabilities, distributed in-memory data grid capabilities, streaming and complex event processing, and we're going to touch base on a very cool product we have, which is the plug-and-play Hadoop Accelerator. What is in-memory computing? Now, you can probably Google it, and there's a plenty definition of what it is. In the most fundamental way, in-memory computing is all about moving data from slower medium, such as disk and sometimes tapes or flash devices, to memory, to a DRAM of computers. When we're talking about SSDs or flash or disk and tapes, we typically characterize them as the block devices, because some of them can range in performance. The tapes obviously extremely slow, and it's almost never used today. But the disk and SSD, especially on the flash and PCIe, can be pretty fast. Still, it's an external device. Still, it's a block device. But you access this device by essentially block reads, and that's fundamentally different from a byte addressable DRAM, the RAM you have in a computer. So, memory computing, in the most simplistic way, is technology that allows you to move data, a large amount of data, from those block devices, flash, spinning disks, to RAM of computer, to DRAM of computer. Why do we do this? There are two fundamental reasons to do that, and they're pretty obvious for everybody: high performance and low latency. Now, we tend to often confuse these two terms. The high performance means how fast can I execute a single task, and low latency or throughput means that how many tasks I can execute in a given time frame, let's say per second. So those two items, the high performance and low latency and throughput, those are the key reasons why people adopt in-memory computing. Now, the reasons behind that, the essentially fundamental technology to achieve that obviously lies in the fact that RAM is dramatically faster than any kind of block device you can imagine. Based on a variety of different measurements. The RAM is faster by anywhere from thousands and sometimes millions of times. We're talking about multiple orders of magnitude. We always give this example that if you think of a RAM as a jet fighter flying in the skies, your typical SSD or spinning disk would be a banana slug in your garden. That's the relative difference in human terms between speed of RAM and speed of disk. Faster than disk and flash, we already established that, but I always frequently get asked this question: isn't flash, fast enough? Well, flash is faster than spinning disk, clearly. Flash is still a block device, and one of the interesting examples to understand why flash is nowhere near the speed of RAM is to understand a chain of events that happens when your application needs to get a piece of data from a flash. Imagine you're writing, a Java application and you need a certain object by a key, let's say, or some kind of an object to get. And if object resides on the disk, now imagine the chain of events that needs to happen. So your Java application needs to make a call to operating system, to system call. The operating system makes, a low-level call that goes to the I/O controller on the motherboard. The I/O controller on the motherboard contacts the device, and device has a seek time. So the device finds the piece of data, either it's in a flash on the spinning plates, and all the way back to exactly the same chain. Now, after this, marshalling and demarshalling, because naturally your Java application stores data in object format, your disk or flash device stores it in the byte arrays, or essentially blocks. So there needs to happen marshalling and demarshalling. So when you add all of this, that's a fairly significant change. Now, the only thing that's changing between spinning disk and the flash is this last item on this chain of events, which is the seek time of a device. So naturally, flash device is a lot quicker. But you still have the entire chain. Now, compare this and contrast this with what's happening when you have just a memory. If you have your data right there in memory, the same process, when you need to access this piece of data, you only do one thing. You do the pointer arithmetic. You just point to a different location in the RAM. So that's the difference between nanoseconds on a memory side and milliseconds, if not sometimes seconds, on the external device. And this is the good explanation why RAM as a byte addressable DRAM is so fundamentally different from a performance perspective from any other external block device, such as spinning disk or the flash devices. Another bullet point on the slide is cost effective, and it may sound like a surprise to many of us, but memory is becoming very, very cost effective. As a matter of fact, if you look at the diagram for the last, let's say, 10 years of the price trends on the RAM, in DRAM, like DDR3, for example, the price of RAM dropped 30% every year and a half. It's exactly the same trajectory that a spinning disk and a flash on. It reduces in price in about the same rate as all those devices. Major analyst firm like Gartner and Forrester will tell you that if you amortize the cost of RAM over 3 years, it's about the same price as a spinning disk or the flash device. Because RAM requires a lot less power, it generates less heat, it breaks a lot less frequently, it requires less space, and on and on and on. So if you amortize the cost, the entire cost of ownership between disk and flash, for example, and RAM over 3 years, it's about the same price. Another interesting point is that, we kind of losing the track of what actually is actual physical price of RAM. And when I present in the audience, I always keep asking the question, let's imagine, you need to have a terabyte of RAM. And you want to split it across, let's say 5 blades. So each blade has about 200 gigabyte of RAM. How much it will cost? How much this cluster with the 5, let's say 10 blades, each blade can have 100 gigabyte. How much this cluster would cost today in today's money? What's surprising to a lot of folks that the price today, little in December of 2014, is about $25K. $25,000 buys you about a terabyte of RAM, including all the computing power around it, including all the network gear you need for this simple cluster. Just to give you the perspective, just a few years back, about 4 years back, the entire working set of Twitter, which is about essentially the week's worth of all the tweets, was about 4 terabytes. So you can literally, for the price of about $100,000, can have the entire working set of Twitter back 4 or 5 years back and have it completely in RAM. So the cost of RAM, although it's still not free, but it has come down dramatically. And the point we're trying to make about it being cost effective, I think, is extremely valid. We at GridGain seen it firsthand, where cost of memory really, has become a non-issue. Versus, literally 5 or 7 years ago when we were just starting, it was an issue. Distributed or not, the whole discussion about distribution in memory computing, again, is a source of confusion. Why are we talking about distribution? Because the whole premise of this presentation about in-memory, and we already established that in-memory means moving from block devices to RAM. Why the hell do we talk about distribution? Again, this is a very frequent question for anybody who talks about in-memory computing. Now, it's an interesting kind of historical look back. If you look back to beginning of mid-90s, literally almost 2 decades ago, when in-memory computing was just starting, there was no way to put enough RAM in a single computer to make it anything useful. If you remember back, it was 16 and 32-bit CPUs. You cannot really address any memory on a single computer. So from an early day of memory computing, from the early days of distributed caching and memory computing, all those technologies, vendors and projects had to develop massively distributed capabilities, because the only way you can basically collate enough RAM to do something useful was to connect many computers together and use their RAM as a one single virtual pool of memory. That's why, unsurprisingly, in-memory systems today represent the most sophisticated, most advanced distributed system in existence. That comes as a surprise to a lot of people. It's not databases. It's not any other systems. In-memory systems from a variety of different vendors represents today the most sophisticated distributed systems that have ever been developed. I'll give you an example. At GridGain, our largest client, company in London, runs us in 2,000 nodes in a full transactional topology. I will challenge anybody to find many other projects that can boast that level of deployment. And having multiple thousands of nodes in the same topology in full transactional topology is a big deal. And in-memory systems were forced to be designed this way decades ago, and they really matured over this time to be one of the most advanced distributed systems in existence today. Now, the next bullet point, caching, streaming, computations. It's interesting to understand that, although we think about in-memory systems predominantly as a data management systems, in the last, let's say 5 years, that has changed dramatically, because the in-memory systems start getting a lot of steam behind them, a lot of momentum, and all of a sudden the use cases starting to get a lot more advanced. So people start basically doing not only storing data in RAM, they were starting to basically do streaming processing. They were trying to couple this with a complex computations that are fully parallelized and distributed. They were start talking about things like affinity collocation, where we collocate data in computation for a high-performance local execution, and all of those different things. So when we talk about in-memory computing, don't just think about it as simple caching or simple data management. Most of today's advanced in-memory systems, and GridGain and Fabric is a prime example of that, support a variety of different paradigms in how do you process data in RAM, not only storing it in RAM. Naturally, when we talk about the complex querying capabilities, SQL comes to mind, and SQL structured and unstructured, essentially, access to the data in RAM is becoming a norm today. It goes without saying, especially when it comes to SQL. And most of the in-memory computing products, GridGain, no exception here, support full advanced SQL capability. Not only localized SQL, we also support very advanced distributed SQL capabilities. We'll talk about this as well. One of the biggest questions that anybody asks, and what's one of the last points in the slide, is the memory is volatile. What happens when when I unplug my computer and then the RAM basically goes away. Well, technically it is true, and naturally it's been true for the last 50 years. We're just about to, develop a non-volatile RAM, but until it happens, RAM is volatile. So in-memory computing systems have developed a very sophisticated mechanisms how to essentially work around this issue. Anything from keeping multiple copies of a data across the cluster to have a variety of different forms of persistence to a disk or flash device, whether it's asynchronous, asynchronous, block level, or not. There is not a single product today in the market that wouldn't provide a sophisticated means to deal with the persistence and volatility of RAM. So surprisingly, for a lot of folks, I truly believe that the question of volatility of RAM is completely non-issue. You can be as persistent or as non-persistent as you need in your application. You can keep everything in RAM without any backups. If you don't care about the data, it can be easily recreated, or it's just very short-lived. Or you can have all kind of persistence and guarantees, multiple nines uptime for your data and for your data consistency if you need to. So that's not an issue at all at this point. The last point on this slide, and again, we're talking about broadly about memory computing, and we kind of broad strokes in different aspects of it, just to give you our understanding of the field. It's a topic of OLAP versus OLTP use cases, essentially transactional analytical processing. Traditionally, and probably would say historically, in-memory computing was used for transactional processing because that's where you needed all the performance. Your trading, your transactions, your advertisement, your website servings, things that basically need a high performance processing typically were transactional use cases. And that's historically where in-memory computing really came about. In the last maybe 10 years, again, it's a fairly large time period, but in the last maybe a decade, these lines kind of blurred. And most of the products today, and again, GridGain is not an exception, natively support both transactional and analytical payloads. Naturally, transactional are a lot more complex to support because analytics means no transactions and lacks the performance and latency responses. So most of the in-memory computing products, and GridGain specifically, has been designed from the ground up as an OLTP system for transactional processing. And over time, we added some of the features to support a non-transactional analytical processing. So bottom line today, most of the products, and again, GridGain is a prime example here as well, we support both OLAP and OLTP, analytical and transactional processing equally well. So let me jump to this slide, and let's talk about now what do we do at GridGain as far as in-memory data fabric. In-memory data fabric is essentially a piece of software, is a piece of distributed software that slides in between your data sources and your applications and provides you all capabilities and advantages of memory computing, high performance, low latency, as well as a variety of different services, anywhere from automatic and very advanced fault tolerance, management and monitoring, ability to run locally on your private data center, or private cloud or public clouds, high-end security capabilities, and a variety of different auxiliary services that we provide. Naturally, it provides the main services which we're going to be discussing, like the data grids, streaming, clustering, computing, and Hadoop Acceleration. Now, the few interesting things to note about this kind of architecture. Immediate question you're going to be asking, how's it different from in-memory databases, for example? And the difference is pretty stark. In-memory databases typically would require you to rip and replace your existing database. Let's imagine you have your Oracle database, let's say Microsoft Server database, SQL Server, and you want to install a new in-memory database from some other vendor. What you end up doing is you have to rip and replace your Microsoft Server or Oracle with someone else's Snowflake. And you probably know in your own company how next to impossible would be to replace such an ingrained technology as a database. Even if you stick with the same vendor, for example, Oracle, you still need to have a very significant upgrade. If you want, for example, use Oracle's in-memory apps, you have to upgrade to Oracle 12c. Not only it's a massive license cost, it's actually a fairly significant upgrade path. Not to talk about if you want to switch the vendors, that's an enormous task. Now, the difference between this and Fabric is that Fabric requires absolutely no rip and replace. It works with existing data sources, whatever they are. It could be any SQL data source, any NoSQL data source, or even Hadoop in our case, which is very unique to GridGain. And we basically work with any data source. The only thing we require is a small change in your application level. Your applications now have to talk to Fabric instead of talking directly to data source. It actually has a secondary kind of benefit as well. It kind of isolates you from direct connectivity to data sources. It gives you a level of isolation. And we take a full advantage of this in Fabric itself. Not only we preload some of the data that you frequently access from data sources, we actually allow you to execute logic right in a Fabric. So you don't have to constantly load data from data sources to your applications to be processed. You can delegate as much processing of this data back to the Fabric where actual data resides. And that gives you a dramatic performance boost because you don't move data anymore. You have ability to essentially keep the data in a Fabric and have all the different type of processing from streaming to compute to kind of cluster computing to traditional SQL and data grids, all within the Fabric. So your applications can essentially just tell the Fabric what needs to be done. It will do it and will give you back just the result instead of basically in many cases, shuffling data back and forth between application and data sources. Okay, so at this point, I'm going to switch to the next slide, and we'll talk about kind of the first base capabilities of Data Fabric. As I mentioned to you, there are four major areas of functional areas, if you will, within the Data Fabric. And clustering compute is one of them, data grid is second, streaming and complex event processing third, and Hadoop Acceleration is fourth. So we'll talk about the first one, cluster and compute. It's a very important function area. It's actually foundational base set of functionality, if you will, in our product. As I mentioned to you, any in-memory computing system is distributed by default. And clustering and compute capabilities define this distribution. We have very unique technology at GridGain that define this capability. First of all, zero deployment. If any of you ever work with distributed systems, you would tell me right away the biggest problem, number one problem in those systems is time-consuming and awkward deployment and provisioning procedures. You write your code, you make a change in the line, then you can press a button and certain scripts go for minutes and minutes and minutes of deploying, copying, building libraries, starting, restarting instances, nodes, and everything else. That's typically where you waste a lot of time in your development phase. We developed zero deployment, which means exactly that. You have absolutely no deployment steps. Every deployment happens on demand, completely transparently to you as a developer. You essentially just write the code like you would do in any IDE or in any text editor, whatever rocks your boat as a developer, and simply run it on one node. Let's say you're starting a node and you join the cluster with multiple nodes, and whatever you run will automatically distribute itself across the cluster where it needs to be executed. So you have absolutely no steps. You don't have to run any Maven, no Ant, none of this. You basically completely shielded from a deployment process. And we're taking care of this very effectively because if you know anything about Java, we have very complex class loading mechanism that's fully distributed, and we have ability to class load on demand any bytecode from any node properly versioned in the cluster, and maintain that versioning, and automatically unload those classes and bytecodes when we don't need them anymore. Very sophisticated system and inside of it, but from a user perspective, from a developer perspective, tremendous benefits, tremendous development productivity tool. Pluggable SPI design. Nothing in GridGain is put in stone. Essentially, every subsystem, and about 15 of them, by the way, 15, anything from discovery, communication, failover, load balancing, indexing for SQL, any of those systems are completely pluggable. Think about GridGain as Lego blocks. You can take any Lego block and replace with something else. Many of our customers and users, which are thousands of them, replace a variety of different components with their own implementation. Frequently, it's communications. Frequently, it's discovery. Could be a failover. Could be a load balancing. You can plug your own algorithms right at the heart of GridGain without ever changing your specific application code. And GridGain will basically adapt its behavior based on your own implementations, your own algorithms. Naturally, every of those subsystems comes with a default implementation we supply out of the box, sometimes a couple of them. So everything works right there when you download it. But you have a tremendous configurability and flexibility in a product built in. That's why GridGain is, undoubtedly #1 OEM platform for in-memory computing. It can adapt to practically everything. We've seen examples. We've seen companies running us on the PlayStation 2. We've seen companies, basically running the entire cluster over emails because they re-implement communication over SMTP and POP3. So a variety of really weird and edge case examples. But guess what? No matter how weird and edge case it looks, GridGain just continues to work. And that's a great testament to how GridGain can be customizable and configurable. Full cluster management. It goes without saying. We pride ourselves that we expose the functionality of a cluster management to you as a developer. We always keep joking inside that about maybe 15–20% of our customers use GridGain just for cluster management. That's how simple and easy and elegant it is. It runs everywhere. It runs on your laptop, runs on your local network. It runs on Amazon Cloud, runs everywhere completely transparently. Nothing to change. We have a multiple implementation. Now talking about the compute side of things. We have multiple implementation for fork, join, MapReduce. As a matter of fact, we have 3 MapReduce implementations in our product. One for a memory use, one for a Hadoop acceleration, and one for streaming. We also have direct support for fork and join. We have support for cron-like task scheduling, so very traditional computation problem. If you have task you want to schedule, just use a cron syntax to schedule it. We support state checkpoints. Very interesting, unique capabilities of ours. Essentially, we developed that as a request from folks that were doing the bioinformatics. Almost everything people do with bioinformatics is taking a long time, and they ask us to basically develop something that, if a task takes 2 days and it crashes in the first 8 hours, they don't want to repeat it from the beginning. So we developed a system where you can basically give us a state checkpoint. You can checkpoint your task, let's say every minute. And if it crashes and it's getting restarted, it can restart from the last checkpoint. So you don't have to start from the beginning. Very cool capability, especially for the long-running task. Pretty edge case, but nonetheless, if you have long-running tasks, this is a lifesaver during development and production. We have very advanced capabilities of early load, late load balancing. I don't have time to really go into detail of this, but ability to have a manual kind of early load balancing and have automatic rebalancing, which is called late load balancing, just at the point of execution. Very advanced feature that allows us to have next to optimal load on a cluster or use server cluster. We obviously have automatic failover. That goes without saying. Particularly any distributed system today would have automatic failover as well. So let me show you some piece of code here. This is basically how simple the closure execution looks on the cluster. So this is the entire Java code. By the way, if you download GridGain, just download. It's free. It's Apache based, and you can look at all the examples right there. But this is a simple code. This is Java 8. This is exactly the entire source code. Just copy and paste it, and it's going to work. What it does is very simple. So it has a main function in a try block. Hopefully, most of you guys can follow Java code. You essentially say GridGain start, supply configuration file. That's where this particular code will join the cluster as a node. And the next thing you do is you're broadcasting the closure. That's as simple as this. Look at this. When you say compute.broadcast, you literally just broadcasting the closure. And if you just type it in, copy and paste, and run it, it's just going to work. You're going to see hello world on all the nodes you have in the topology, whatever the current topology is. It's kind of a lot kind of awkward to explain it on a webinar, but you guys can try it, and you're going to be amazed that you didn't do any deployment steps. Remember I told you about zero deployment. This is exactly how it works. You just type this, click run, absolutely no copying, no moving jars anywhere, no deployment step, no end, no maybe nothing. Everything is going to work automatically here. And that's how you can develop. You change the code, click run. You change the code, click run, everything just works. Very cool stuff. I highly recommend to try it out. So let me switch to in-memory caching and data grids. Yeah, we kind of use caching and data grid interchangeably. Now, this is probably the bulk of functionality at GridGain. It's a lot. Even if you look from a code perspective, it's probably the biggest code chunk we have on the product to support that functionality. So what is data grid? It's kind of interesting to understand data grid in comparison to kind of comparing it and contrasting it to the compute grids. So the compute grid, we just discussed, essentially is the ability to parallelize processing on a cluster of computers. So data grid is essentially about parallelization of a data storage on a cluster. So how do I take a large data set and split it across multiple computers? So obviously when you do that, you open a whole can of worms with a lot of different problems. How do you transact? How do you failover? How do you partition properly? How do you do this? How do you do that? How do you load balance? There's myriads of problems, and data grid is essentially designed to solve that for you as a developer, so you can have a very simple API, just enjoy the capabilities. So what do we have here? So fundamentally, the GridGain data grid is based on a key value store. It's a very important fact because the key value is the fundamental data structure that can be molded into any other views. We have multiple views on the same data. For example, you can look at data grid as a key value store, right? You have a key, you can get the value. We also have a file system view over exactly the same data. You can view data grid as a simple file system. Just literally open file, read from it, write to it, do whatever you want to do. We also have a SQL view. So exactly the same data that you have on data grid can be viewed as a SQL. So we actually supply the whole JDBC driver. You can just open the connection and start doing selects for the same data. So exactly the same data, by the way, we have also HDFS view, which is a specific Hadoop file system on exactly the same data. So having a fundamental data storage model as a key value is a huge benefit for us because we can provide you a multiple views in the same data. We support replicated and partition data storage modes. Again, in and of itself, it's a huge topic, but in simple terms, replicated mode is where each node in a cluster has exactly the same data set as everybody else. So naturally, your entire storage can be only as big as the single node, but it gives you tremendous read performance because any node in the cluster can have the same data, can answer the same question. But in reverse, it has very bad write performance because every time you update something, you have to update on all the nodes. But you'll be surprised how frequently people use this mode because there's plenty of data in businesses that are mostly read-only and infrequently updated, and they need a very fast read capabilities. You know, a typical example would be in financials with master data sets. Partition is what basically people use most of the time, because it's a most balanced approach. In a partition case, data is partitioned across all the nodes in a cluster, especially those that participate in data grid. So let's say if you have 6 objects and you have 3 nodes, each node will have 2 objects stored in a most simplistic way. Now, the third bullet points here about terabytes of data of any type. What I want to say here is that we kind of often get asked the question, what's the typical size of a memory computing system? And it typically relates to data grids because that's where you store in data, and data grids often play a role of a system of records. And what I typically respond is that there's no minimal limit. I mean, obviously, if you have just a few megabytes of data, you don't need any memory computing. You can keep it on your iPhone. But typically, we're seeing from hundreds and hundreds of gigabytes of data sets to lower teens of terabytes. So anywhere from quarter terabyte to 10, 15 terabyte. That will be kind of a sweet spot for today's memory computing, both from a cost perspective and from software perspective. I don't think there's any single in-memory computing system today that deals with petabytes of data. It's just cost prohibitive. and that's typically a area of data warehouses like Hadoop. Okay, we have on-heap and off-heap storage, and that's actually one of the most, well, not the most, but one of the important features. As you know, as if you guys work in the Java world, you know the problem with garbage collection in GC cycles. So typically, Java cannot work very well with the heap storage, anything above, let's say, 10, 16 gigabytes, because your GC pauses will become very large, and you cannot maintain any SLAs. So what we do essentially, we develop the whole off-heap management, memory management. So essentially, if your computer has a 96 gigabyte of RAM, you can allocate 8 gigabyte of this to a Java heap, essentially have some on heap place, and allocate the rest of it to off heap. And GridGain will automatically manage this off heap memory as well. So we have essentially our own memory management system, very similar to Java's, by the way, that we manage ourselves this big chunk of RAM. The beauty of this, there is no garbage collection there, cycles that are happening there, and therefore we can still utilize the entire RAM available in the box, but not be subject to garbage collection. So we have a backup replicas automatic failover. Those are mechanisms for your kind of solving the problem of failover, and it's not precisely persistence, but that's the mechanism to basically how do you protect against a server crash, because it's all in memory. If the server crashes, then in memory disappears. So you get multiple replicas in a cluster, so your particular data set can be stored in more than one node in a cluster, and we automatically fail over in case of one server crashes. We'll pick another master and do all the right things. One of the key functionality of Dedicated is distributed asset transactions. We hold an absolute record in the performance of asset transactions. Not only we have one of the best in mature implementation of full transactional behavior, we hold an absolute record. About a year ago, we achieved 1 billion transactions per second. I'm talking about the billion with a B on 10 commodity blades on a terabyte of data set. It's an unbroken record, and we hold the record here, and we're pretty confident that our implementation of a full transactional behavior from a performance standpoint is a market leading today. As I mentioned to you before, we have a SQL query, we have a full SQL support. So if you're into the SQL, sometimes SQL is the best answer. For example, if you not doing the computations or simple key-based access, if you want to do some some interesting access like with the joins and complex where clauses, it's a lot easier to do it through SQL than kind of write down your own full scan queries. We have pluggable indexing capabilities as well, a very advanced feature. You can develop your own store procedures in Java or any JVM language. So this whole set functionality is extremely deep and very comprehensive here as well. So what I'm going to show you right now is a piece of code, and this is like you can find a bug. I'm sure some of you will find it. But essentially what it does, it's just a quick example of how easy it is to use DataGrid. So essentially the same story as before. You say in GridGain start, that's how you join the cluster, and then basically you getting a cache, which is, think about it as a table called account cache, and what you do essentially is an account with ID 123. We credit $20, I guess, to it, and if it's not there, we start this account with $20, and we essentially put it back into the data grid in the last line. So naturally, there's a bug in this code, and I'm not going to wait for a long time. Essentially, the bug is not transactional. So all these operations between get and put have to be in one transaction. So if you fix it, and fix is extremely simple, just look at this code right here. So all you can do is just to say cache and tx start and put it in a try finally. I mean, it's Java 8. In Java 7, you do it in try finally. But essentially, that's all there is to it. You just basically wrap it in transaction, and it will be absolute transactional behavior. Keep in mind, this is completely distributed system. So this transaction is not local. It will lock this account 1, 2, 3 anywhere on the cluster, depending on your isolation level and whatever you configure it in the transactional behavior. But this is exactly the same transactional behavior in semantics as you would expect in a normal database like Oracle. GridGain supports optimistic and pessimistic transaction modes. It supports all isolation levels, read committed, read uncommitted, and even serializable. If you want to have an absolutely robust transactional behavior with serializable isolation level, you can have that with GridGain, which is extremely unique in a product like in-memory computing frameworks. Okay, the next thing I want to talk to you about is in-memory streaming in complex event processing. This is a very interesting area, and you can think about this, why is it different? And it's different. It's actually dramatically different because what is streaming? The streaming essentially means there is no end and there is no There's no beginning and end of the data stream. It's constantly coming in. And since it's basically a non-finite data stream or data set, none of the existing approaches like your SQL or MapReduce, for example, would work. Because for all of those techniques, SQL and MapReduce, for example, or traditional NPT processing, you have to have a finite set of data. In streaming, there is no such thing. So over the years, basically, we've come to the realization that in streaming, you have to work on a sliding window. And a sliding window essentially is, you can understand very easily, like last 5 minutes of events, last 5 something. So it's always looking back, last something. And again, typically this window is programmatically defined, and that's the case in GridGain. You can programmatically define. We have many windows that we supply automatically. You can just write your own function and tell us what the window is. And then you define functions that work on that window. So for example, we have a customer that does fraud protection. It's a payment customer, a payment processing company, I'm sorry. And what they do essentially, they have this massive stream coming in. They parallelize the processing of it on a GridGain cluster. And what they do essentially, they're looking for a certain patterns within a 5-minute window. So they define a 5-minute window, so every event has a timestamp, and they, in a window that they have, is always have a 5 minutes worth of events, and they're looking for certain patterns. And they find the pattern within that window, they trigger a certain event, and it goes further for processing. So we have lots of different capabilities in this, and that's what's really unique about GridGain streaming support is we're about the only product that supports both streaming and a complex event processing. So we support pipelining as well as CEP, complex event sliding window processing. Typically, it will be 2 different products, and we just have the capability in one. So we support branching, pipelining. It basically think about the event processing as a pipeline. Events coming in, they go this processing unit, this processing unit, this processing units. You can, you can programmatically define this pipeline. We have pluggable routing, which basically are able to route events between different processing units. I already mentioned we have a sliding window. We also have at least one guarantee, guarantee. Basically guarantees that no matter what, events will be processed at least once. So you're not going to lose events. That's a very interesting capability as well. So it's a very interesting use case. We're starting to see more and more of these use cases coming up. Naturally, with all the mobile and wearable devices coming up online in the next couple of years, especially wearable devices, we're going to see dramatically more streaming use cases than we see today. So today, it's a small part of what we see, but we already have technology where we constantly maturing this. We're constantly looking at feedback from our users and customers, and we're constantly putting more and more thoughts and code into this area. So we're going to see a lot more advances in this area as well. The next thing I want to talk about is our Hadoop Accelerator. And probably we can spend the next hour talking about just that, but we have just a few minutes left, and I want to kind of quickly say what we've done. So essentially what we did, we developed a plug-and-play Hadoop Accelerator. So essentially, without any code change, without any changes whatsoever, you can take your Hadoop installation, whatever your code is written in Pig, Hive, straight MapReduce code, and we're going to be able to accelerate that. The way we accomplish this is the Hadoop is based on 2 fundamental technologies, the HDFS file system, distributed disk-based file system, and MapReduce, which is essentially a framework to parallelize processing all this data. We developed the in-memory versions of two of them. We developed a GGFS, which is the in-memory file system that's fully compatible with HDFS. It can work in two modes. It can work as a caching layer on top of HDFS, basically work read-through and write-through the HDFS, or it can work as a standalone file system, bona fide standalone file system that fully replaces HDFS. We also we provide a MapReduce implementation, yarn-based MapReduce implementation that takes advantage of entire in-memory infrastructure that GridGain provides. It does all the in-process data collocation, very cool stuff, like a test, like Apache test, but in a more advanced way. We also do, instead of polling, which is the fundamental problem with Hadoop, we do eager push scheduling. So there's absolutely no loss of performance anywhere because of the polling. And the next slide, it's a good picture to see visually how different is our processing of Hadoop, basically based on GridGain and versus the standard processing of Hadoop. If you look at the gray lines, dotted lines, this is the standard way how Hadoop does its own execution. So Hadoop client contacts the job tracker, and everybody contacts name node. Essentially, name node is kind of a single bottleneck in the Hadoop installation. The job tracker now basically produces a bunch of tasks, and the task tracker pulls, gets the task, and then spawns the process that actually does the MapReduce job and all of this. Plenty of communications, plenty of polling. Everybody contacts name node for different reasons. The solid line, the blue line, represents just what happens in GridGain. There's none of this. We do away with job tracker, task tracker, and name node. And we have a direct connectivity between GridGain client, how do you submit your task in Hadoop, right to the GridGain data node that contains data in RAM, in memory, and we're going to collocate the execution logic right in the same process. So absolutely streamlined processing, no name node, no network noise, data collocation, and eager push scheduling, as I mentioned in the previous slide. All of this allows us to claim anywhere between 2 to 10 time performance increase on certain types of tasks. Now, what we do get asked quite a lot is about how do we different from Spark, because we kind of solving the same problem. And we actually love the Spark. We're both part of the Apache family and Apache Software Foundation family, but we're solving a single problem in different ways. Spark really requires you to essentially, it's a new ecosystem. You have to move your data from Hadoop to Spark cluster, and then you can process data in the Spark cluster. Then you have to move data back from Spark to Hadoop. And that's the biggest kind of awkward part in the Spark ecosystem, that you have to move data physically. You have to move data. Not only it's awkward, it can be very time consuming. So the difference between, so GridGain does it differently. With the GridGain's Hadoop Accelerator, we require absolutely no data movement. We do everything plug and play in place. If you have your data in Hadoop, keep it there. Just install the GridGain cluster just as you would install, just the same way you would install the Spark cluster. But the GridGain cluster, GridGain software works on top of the Hadoop, maybe not on top of, but along the side of Hadoop, and does everything plug and play in place. That's the major difference. So, for example, if you have your peak and hive tasks, instead of basically moving data to Spark and rewriting everything from scratch in Spark APIs, you do nothing in GridGain, and things just work faster as you would in Spark. The last slide I want to mention is that I'm going to show you some quick screenshots of our management capabilities. Naturally, when you have dozens and dozens of nodes in your cluster, the management capabilities become an absolute necessity. It's very hard to run blind multiple nodes, let alone tens and sometimes hundreds of nodes. We have one of the best industry, and I can say with a straight face, one of the industry best management and monitoring capabilities. Very comprehensive, real-time app that shows you up to the millisecond events. We have a variety of diagrams, charts, and almost everything you can possibly imagine, from telemetry to SQL execution from right there. All the details of a data grid, streaming, computational processing, where your tasks are, what the states are, the ocean of information for anybody in development, specifically in DevOps, in production. It's an awesome tool to have. We use it every day in GridGain when we develop ourselves, and majority of our customers and users as well use it as well during development and production. So Dan, I think it's my last slide, so I'll forward back to you.
Thanks a lot, Nikita. Sorry, I was on mute there. So let me go ahead. I know we've got a couple of questions here, so let me pull those up real quick here. And, we're getting pretty short on time, so I'm going to, go to what looks like the most significant questions. And here's one for you. What's the difference between Apache Ignite and Spark?
Well, as I mentioned, I already kind of answered this during the presentation. Be very quick. The difference, again, is, in fact, that Spark would require you to move data from Hadoop to Spark to be processed in Spark cluster. The GridGain does not require any data movement, and we don't require any rewrites. So if you have your Hive task in Spark, you have to rewrite the Hive in either Spark SQL or Spark APIs, and they have to move data out from Hadoop to Spark and then all the way back if you want to store it in Hadoop. In GridGain, you don't have to do any of this. If you have your Hive task, just run it. As long as you install GridGain alongside of Hadoop, things will go faster. That's the fundamental difference.
Great. And we've got a few more questions here. I guess this one, well, here's another comparison question. What are the main differences between GridGain or Apache Ignite and Hazelcast?
Yeah, the difference probably would be just a breadth of functionality. We support not only data grid, we support a clustering computation capabilities, we support streaming, we support Hadoop acceleration, and undoubtedly we have the dramatically more faster and more performant a transactional engine than Hazelcast. That will be probably the main differences between us.
Okay, great. And what other languages other than Java are supported?
We support any JVM languages, Java, Scala, Groovy, and we also have clients for non-JVM languages for C++ and .NET. So essentially, any JVM-based language plus .NET, again, any .NET language, VB.NET, C#, and the C++.
All right, excellent. Now, you just mentioned .NET, and I'm not sure if you answered this question too in the course, and this is a bit of a technical question, but here it is. Does GridGain.NET support, reading the message here, require Java persistence logic, or can it work with .NET persistence logic? Does this question make sense to you, Nikita?
Yes. I'm not sure what exactly .NET persistence is, but I'm pretty sure that we do support .NET persistence because we have a bona fide, a native .NET client. So it's not some kind of, a call through to Java. We have a native .NET code for our client that was written and developed by us. So whatever .NET persistence is, I'm not sure the terminology is correct here, but I'm pretty sure we support that as well.
Okay, excellent. Now let's see. I'm just scanning through the questions here, and I want to give you the best, most relevant ones. Well, here's a good one. How can one contribute to Apache Ignite?
Very easy. Apache Ignite is Apache project. So just contact the PMC for Apache Ignite and indicate you're interested in being a committer, and I'm sure we're going to be, the Apache PMC will be more than welcome. We already have a significant community behind the project, and it's constantly growing, by the way, from a variety of different places, from different companies. So absolutely welcome It's an awesome project. It's one of the rising stars in the Apache community, and it's an excellent opportunity to participate.
Okay, great. And here's another one. How does GridGain work in cloud environments?
We worked with absolutely no difference than with no cloud environment. We're completely agnostic to where we deploy. We have a special support for cloud, specifically for discovery, because on the clouds, typically IP multicast doesn't work, and IP multicast is a default way for discovery. So on the clouds, we have a different way, which is basically TCP/IP based. And for example, on Amazon, we have a specific support for Amazon clouds through S3 discovery, S3-based discovery. As you know, on the clouds, the biggest problem is that IPs is changing constantly underneath of you when you start nodes or images. So we have very interesting and very easy to use S3 discovery that basically eliminates this problem. So yeah, bottom line, I would say about 30% of our customers and users runs on the cloud. So there's absolutely no problem, and we work beautifully in the cloud.
Okay, excellent. And let's see, here's a couple that actually have just come in. So what is the difference between GridGain versus InMemory database, like NuoDB, NuoDB, if you're familiar with that?
Yes, yeah. So the difference is, that's a good question. And that's something that's, get asked a lot, and it's fairly confusing. So NuoDB or any other distributed and or in-memory databases, there are databases. They're essentially a SQL databases, maybe NoSQL databases. But they are just a database. They have no idea or no notion, I would say, probably, about streaming, about clustering capabilities, about compute on the clustering capabilities, or let's say Hadoop acceleration. And as I mentioned in the very beginning of the presentation, when you talk about a database, if you want to deploy it, you're essentially talking about replacing existing database. And always keep this in mind. When you're bringing up a new database, you're replacing existing database because you have to move your data from one to another. Fabric was designed to work above any data sources. We do not replace any existing databases. You can move data into the Fabric and have Fabric as your system of records, but that's completely optional, and it's driven not by a physical requirement to replace one with another, but it's driven by your needs of your applications. It's a very different approach. So we typically come into a customer and say, well, you have your Oracle database, keep it. We're going to optimize it. We're going to make it a lot faster. Down the road, you can decide if you want to move certain data sets into the Fabric and have them there as a system of record. That's perfectly fine because we support the same SQL, pretty much the same capability. But we do not require you to replace anything. And that's a much easier way, much smoother, app ramp to in-memory computing than coming in and say, drop your entire database infrastructure and replace with us. It's a very hard sell, and it's just technically, and from a product management perspective, is not, not a smooth way, not a right way to do it. Just obviously, in my opinion.
Okay, great. Good answer, Nikita. Now, there are a couple more questions, but it doesn't look like we'll have time. You'll probably get cut off in the middle of those answers. So I just want to let everyone know that if you ask the question that didn't get answered on this call, we will send you responses after the fact. So with that, I want to thank Nikita for his presentation today. Excellent job, and we want to thank all of you for taking the time to come and join us on this webinar. Please do come by the GridGain website, download the open source application. It's easily accessible and easy to install. And again, we really appreciate all of your time, and we look forward to hearing from you again in the near future. Have a great day,
Thank you very much, everybody. Thank you.